Hi, I'm Nupur Thakur from Arizona State University, and I'm here to present our paper Graph of Graph, a nested graph-based framework for early accident anticipation. Our goal of paper is to predict the probability of a potential accident in the near future using the dashcam videos. Dashcams, which are short for dashboard cameras, are installed on cars mainly for determining the responsible parties in case of accidents. So, why is this task important? With the emergence of smart vehicles, accident anticipation is necessary to avoid any potential hazardous events, ensuring road safety. However, this task is very challenging, and some of the challenges are listed here. First, as compared to other road events like lane changes, accidents are rare events. As Second, accidents happen within very few seconds and they vary in nature. Therefore, they need to be predicted quickly to take actions to avoid them. And last, the traffic scenes are generally filled with objects and events that are irrelevant to the task, acting as background noise in this case. For example, there are trees, buildings, cars, etc., that are not relevant to the task and add more noise to the visual scene. So we propose a graph-based framework called Graph of Graph for this task to overcome some of these challenges. We summarize our contributions here. First, we propose spatio-temporal object-level graph for representing the frames. Such graph helps in eliminating background noise. For example, consider the two consecutive frames from a dashcam video here. The bounding boxes in the frames represent the detected objects, and on the right is the spatio-temporal object graph created for each of the frames. As you can see, the graphs model the interactions between the objects explicitly. Also, there is information exchange within the frame through spatial edges and across the frames via temporal edges between the objects that belong to the same class. Also, this way, the background noise from the frame, like the trees or buildings in this case, uh, are excluded. Next, we propose to include the use of spatiotemporal global frame feature to provide the information about the entire scene. And lastly, we propose another graph structure called frame graph, which is built on top of the global frame feature and the object graph, creating a nested graph representation. This graph is useful in propagating the information extracted from the spatio-temporal object level graph and the global features. This is the overall framework of our proposed approach graph of graph. There are three major components for our method. First is the spatio-temporal object graph, then the spatio-temporal global feature, followed by the frame graph, which is built on top of these two modules. So first, given a sequence of video frames, the objects are detected for every frame using a pre-trained object detector, and the object features as well as the labels are encoded to represent the node features in this case. The spatial edges here would be the Euclidean distance between the centers of the detected bounding box. We propose the temporal connections across object frames, object graphs of different frames here, where the edges will exist only between the objects belonging to the same class. The edge weights here are cosine similarity between the object visual features. This ensures that there is flow of information across the frames but reduces the irrelevant information flow across different objects belonging to different classes. After these graphs are formed, these are passed through graph convolution and pooling layers to get a graph embedding that represents every frame. So for the bottom channel, the spatiotemporal global feature is extracted for every frame using a pre-trained network, which is also frozen during the training. This takes a short sequence of frames and produces frame level global features. And lastly, the frame graph is where every node represents a frame and there are connections to previous K frames. The node features here are from the object level graph and the global frame feature. This graph is then processed through graph attention and fully connected layers to produce a probability that accident will occur in the near future. To evaluate our method, we present results on two data sets that contain real-world dashcam videos, DAD and CCD. DAD dataset contains dashcam videos from vehicles in 6 cities in Taiwan, and in CCD dataset, the accident videos come from YouTube and the normal videos are from BDD 100K dataset. We compare with existing methods that use graph representation for frames. We differ in the way we incorporate the temporal information as well as the nested graph representation. The metrics used here are average precision denoted by AP and the mean time to accident, which is denoted by MTTA. From the table, it is clear that our method is able to outperform the existing methods in both the metrics by a large margin. Another experiment we conducted was comparing the global frame feature because baselines use the frame feature extracted by VGG16, which uses spatial information only. From the table, it is clear that when we use our spatio-temporal feature, which contains temporal information, the performance increases. This shows that the temporal information is important for this task. You can refer to our paper for more details on the experiments. So in summary, I would like to say that graph of graph shows how temporal information is crucial for this task and should be included at different frame extraction levels like object graph, frame graph, and the global feature. We also perform extensive experiments to showcase its effectiveness on the real-world dashcam videos. To read our full paper and access our code, you can scan this QR code. Thank you.